Okay, so in this set of slides, we will talk about the continuity equation, a variable called omega, and vertical velocity, and the interaction and relationship between these concepts. The continuity equation is something that you saw when looking at the Ulrich UC Davis dynamics video on the continuity equation the previous week. We will reinforce some of the concepts from that and see how it relates to vertical velocity and this parameter omega, that right here, we haven't talked about yet, but we will. So this topic is general to meteorology, but the strongest reference is with respect to large-scale meteorology, so that'll be emphasized. Okay, so to review the continuity equation, here is the equation that we arrived at from our previous study. The change in density in time, the rate of change of density over time, rate of change of density, is equal to minus the mass flux divergence. And so mass flux divergence is divergence of mass flux. Mass flux is density times velocity. And the best way to illustrate that is in one dimension here. So you have a control volume fixed in space somewhere, and there's velocity blowing into and out of the face. When you multiply velocity times density, you get mass flux. And the units of that are mass per unit area per unit time. So there's a certain amount of mass leaving the volume from side B here over an increment of time per unit area of the face perpendicular to the flow. Likewise, there's a certain amount of mass entering the volume side A from the density times the velocity, that quantity entering the face. So that's mass flux. When you take the net mass flux, that equating what's leaving minus what's entering on all sides of the cube, that's the mass flux divergence. So the way to interpret this equation, though, is when the mass flux divergence is positive, meaning as you go along x, there's more leaving than entering. That's going to be a decrease in mass in the volume, and therefore the minus sign turns d rho dt into negative. So the mass over volume will decrease over time as there's more mass leaving than entering when there's mass flux divergence. Likewise, if everything's opposite, you'd get mass flux convergence and have rho increasing over time. Okay, so here is an example of mass flux convergence. So you have more, sorry about that, right here. There's more mass entering than leaving. So that means grad dot rho v is negative, because if you slide along the positive x direction, the mass flux is decreasing. So you got grad dot rho v is negative, but negative and negative is positive, and therefore d rho dt is positive. Likewise, here's a situation where you have mass flux divergence. So as you slide along the x here, whoops, I did it again. As you slide along the x here, there's more mass flux leaving than entering, or as you slide along x, mass flux is increasing. So that means grad dot rho v is positive, negative a positive is negative, and therefore d rho dt is negative, meaning that density will decrease because the mass per unit volume is less because there's more mass leaving than entering. Okay, so this is the top part of the lecture notes that I handed out on this topic. You should have received it. And it's as we now are pretty clear about, I'm sure, is that continuity equation is about mass conservation. It's as simple as that. And so this is just the same diagrams we looked at. I won't repeat that, but I just want to point out here to emphasize that mass flux has units of mass per unit area per time. So you can see the notes and then also keep reading below and to pick up some of the other details that come up. Okay, so this here is chapters 3.12 of Holton. So you can refer to the text, you have the PDF of that, and Holton is a quite mathy book, and so we actually want to be able to explain the points in verbally, so that we can, in effect, see the forest through the trees and not have to get buried in all the math. But full details, of course, are in the book. But this is the part where we talk about the continuity equation in pressure coordinates. Okay, so the equation that we saw on the previous slide is for the continuity equation in a XYZ coordinate system. Now I want to see what it would be like in an XYP is for pressure coordinate system. Okay, so the derivation is quite similar. We're basically looking at the change in mass over time due to mass flux convergence into a volume, except now instead of delta y, delta x, delta z, we have delta x, delta y, delta p, because p is replacing z as the vertical coordinate. So other things pop up, and then by the time you're all said and done, you get an equation that doesn't have d rho dt in it anymore. So it's not a prognostic equation, it's a diagnostic equation and it reads as du dx plus dv dy, meaning the divergence in horizontal wind on a pressure surface plus this quantity d omega dp is equal to 0. What omega is the pressure velocity. And let's jump to the next slide and I'll emphasize that. Okay, so omega is right here, the rate of change in pressure over time following the motion. That's a total derivative. So as you can imagine, as particles move along the atmosphere, they can move along a path whereby the pressure changes as it moves. So that means omega would be non-zero. So omega is positive when the change in pressure over time is positive. It's negative when the change in pressure over time is decreases following the motion. So we call that the pressure velocity. So omega is defined as dp dt total derivative. Note that the capital D and the small d that I use here, those are interchangeable, just different symbols for the total derivative. So, okay, we got a little cutoff here. Rate of change in pressure following the motion, that should say. And this is analogous to vertical velocity in height coordinates, meaning in height coordinates, the vertical velocity is defined as dz dt, or the change in height over time following the motion. In pressure coordinates, omega is used as the vertical velocity, as the change in pressure over time. Remember that in pressure coordinates, pressure takes place of z as the vertical coordinate system. So omega is analogous to w, the former being for pressure as the vertical coordinate, the latter being for height as the vertical coordinate. Okay, so what we emphasize then is that here's the key equation here for the continuity equation in pressure coordinates. So mass flux divergence or convergence is going to equate to the minus, as we move this to the side of the equation, d omega dp. So we have to kind of get some physical intuition for this. It's similar to what we saw on the earlier slides when we looked at the continuity equation in a height coordinate system, when we looked at mass flux convergence and divergence out of a volume leading to density changes in time. Now we want to see why this also equates to a change in omega over pressure. And so this, we got to go and look at this now. Okay, so before we go into trying to get a better understanding, physical understanding of what omega is, let's just explicitly relate it to vertical velocity for a hydrostatic atmosphere. And so there's some assumptions that are made, and we'll get to those. But remember that omega is defined as dp, d pressure, d time following the motion. So based on what we learned, we can always split up a total derivative into its partial plus its advection terms. And we can do that here. dp dt is equal to d partial dt plus u dp dx plus v dp dy plus w d partial p dz. Okay, it turns out through scale analysis, and you can look at the text on this if you're interested, that in large scale motion, the local change in pressure with time, meaning at a fixed point in space, plus the horizontal advection terms are relatively small compared to the vertical advection term. So w d partial p dz. If we assume a hydrostatic atmosphere, which is kind of the basis for some of the scale analysis that leads to these terms being small, dp dz equals minus rho g. And then we can plug that directly in, plug in minus rho g for dp dz here, and you get omega is approximately equal minus rho GW, meaning there's a one-to-one, well, not one-to-one, but a proportional relationship in a sense between omega and vertical velocity, the proportionality constant being the product of density times gravity. So that's what we boxed here, is omega is approximately minus rho GW. Note the minus sign here, because when vertical velocity is positive, meaning following the motion, you're rising in height. That means pressure is decreasing following the motion. So that means d omega, or dp dt, is negative when w dz dt is positive. Okay. Okay, so now we can delve into omega a little bit more. So what I'm showing here is, remember that control volume from the earlier slide of that box fixed in space with sides A and B on one side and mass flux entering and leaving? Kind of a picture that same box. I didn't draw it in 3 dimensions here, but I kind of superimposed a volume bounded on top and bottom by pressure surfaces. So remember, in pressure coordinates, we kind of look at horizontal motion on a pressure surface. So that's what I've drawn here in the middle, where we got horizontal motion along a surface of pressure. And so the labels for the pressure surfaces may be P naught as some reference pressure, going down a certain increment of pressure as you go higher up in the atmosphere, P naught minus delta P, and this dashed line in the middle might be halfway between those, or P naught minus delta P divided by 2, just to kind of set up the diagram here. And what we've done is we've bounded this box that's really in 3 dimensions that we're just looking at in 2 within this pressure surface. And so we got a box flowing along a pressure surface here. Notice that the rate of change of velocity over x, as you slide along x along the pressure surface, the velocity is decreasing. That means du dx on a pressure surface is negative. So that's how we've drawn this example here. So okay, so here's what the implications of the previous slide are. So as we talked about, we got this volume of air embedded within 2 pressure surfaces, and you have horizontal flux convergence into the volume here in 2 dimensions here. So there's more air entering than leaving, so that du dx on a pressure surface is negative, because if you go along x, u is going less, so du dx is less than 0. So instead of thinking of this as is the density increase or decrease like we already talked about, now we're going to think of it in terms of what does that mean in terms of the distribution of vertical velocity either side of the volume here, and in terms of this quantity omega. And this follows from the continuity equation in pressure surfaces that we brought up on previous slides. So this is the equation we repeated here: du dx plus dv dy all on a constant pressure surface equals minus d omega dp. So let's see if this works out sign-wise. So these arrows here, these brown arrows, these are the vertical velocity that happens as a result of the convergence. And we'll try to see if we can physically understand what's going on here. So as we got convergence, du dx is negative. On the bottom, we have vertical velocity going up. Let's, for example, that means dp dt, as you go up, lower in pressure, velocity, as you go lower in pressure, omega, the pressure is decreasing because the parcel is going upwards and decreasing in pressure in time. So that has it, that's omega is negative. Omega is more negative on top because we got a bigger arrow. So as you go higher in pressure, as P increases, omega becomes less and less negative, or becomes increasing. So we have increasing omega with pressure. That follows suit. As du dx is negative, d omega dp therefore must be positive. And so we have a positive d omega dp indicated by these vertical layers. And so the math you might have to kind of play around with and get more comfortable with, but just looking at this makes sense. As mass piles into the volume, that's going to push, as you got horizontal convergence, you have vertical divergence. So there's kind of a mass continuity here that you can see, which in effect creates vertical velocity as a result of convergence horizontally. Let's see if we can see some other examples of other distributions of vertical velocity that are also consistent. This is not unique. You can think of other situations. Okay, so here's the same diagram. We got the same level of mass flux convergence, meaning more stuff coming in than entering. And here's another distribution of omega that could result, see, a vertical velocity. So you have a small omega or vertical velocity, I mean dp dt is negative here, increasing as you go higher up. The difference is the same, meaning that there's the same level of change in omega with pressure as we saw on the previous slide, even though the arrows are smaller. So by itself, this doesn't tell you the actual value of vertical velocity, it just tells you the distribution of the vertical velocity. As long as d omega dp is of a sign and of a value consistent with the du dx, this mathematically equates, okay? So the point is the continuity equation tells you by how much velocity changes across the volume, but not in and of itself the actual vertical velocity. So we're going to have to do a little more work to pull that out, and you'll see where that comes from. Okay, to make this point even more so, I've drawn the same diagram here, but with downward vertical velocity arrows. So, again, this doesn't give you anything about the actual vertical velocity, but just the distribution. But the same thing holds here. So du dx is negative. As you go positive in pressure, omega, you got a smaller omega here, meaning dp dt is positive because it's going downward now. But it's getting increasingly positive as you go down further. So as you increase in pressure, omega is getting bigger. So d omega dp is positive when du dx is negative. So pressure change following the parcel larger on top than bottom of the box in this example. And all three of these examples actually. So the distributions of omega are consistent, but the actual omegas and the vertical velocities are different on each side. So again, this is just about a distribution, it's not about an actual